So now we're going to move a little bit away from centripetal acceleration and focus in on centripetal force. Okay. And so the classic textbook definition of centripetal force is a force that accelerates a body by changing the direction of the body's velocity without changing the body's speed. So it's kind of like what we were talking before, where we said that, you still have an acceleration even though velocity is constant, because the direction of the velocity keeps changing. Okay, and so given that what we know about Newton's laws, right? How could we find a formula for centripetal force if we know centripetal acceleration? And I think I've already ruined the ending on this. We did it in a previous problem, but I'll look at it again, right? In general, if F is equal to ma, right, by Newton's second law, then centripetal force must equal to m times centripetal acceleration, right? But centripetal acceleration is this guy, right, which means centripetal force should just be mv squared over r. Okay? Does that make sense? I'm just taking my centripetal acceleration and multiplying it by m. Okay? And now, what this sets up for us, so in the next slide, you guys will see that I've just actually confirmed that that's mv squared over r. And what this sets up for us is that we have, in the world of circular motion, we have a new Newton's second law, right? And that Newton's second law is that instead of summation of forces, right, being equal to ma, right? So this is just for the linear world when things are moving, right, in a line. So in the circular world, the summation of forces, or F net, is mv squared over r. Okay? And so for right now, that's going to feel a little bit abstract, but we're going to do 3 to 5 problems in this lesson where you actually do a Newton's second law free body diagram and setting up of equations that shows you exactly how this works. Okay? That's my guarantee to you. All right, so it begs the question, this is on the next slide, what is centripetal force and what causes it? The answer is very simple. Whatever force is causing the object to move in a circle is centripetal force, right? So think of something that's moving in a circle, right? And what force in there where if you took it away, the object couldn't possibly be moving in a circle anymore, and that is your centripetal force, right? So for example, in the case of electrons orbiting a proton, what would be the centripetal force? Well, if you took away the electrostatic attraction, then you don't have circular motion anymore, and the electron's no longer moving around the proton. Okay? So in that case, the centripetal force would be equal to the electric force. What about planets orbiting a sun, right? As you can see in this picture over here. Well, if you took away the sun, meaning you took away gravity, no more circular motion, gravity is causing the centripetal force in that case, right? What about the case of a lasso? Well, if I cut the rope, in other words, I cut the tension, the lasso is not going to be able to spin around in a circle anymore. So in that case, tension is causing the centripetal force. What about the case of a car zooming around a track? Well, if it were ice and not asphalt, I couldn't be zooming around that track. I'd slide off, right? So that means friction must be causing the centripetal force in that case. And what about a roller coaster doing a loop-de-loop, right? In that case, if it wasn't for the track providing a normal force, then the roller coaster would fly off and you would not have any kind of a circular motion. So in a loop-de-loop, it's actually a normal force causing centripetal force. Okay? So the moral of the story is that no matter which case, if you have some kind of circular motion happening, there's some force keeping it moving in a circle, and that force is giving rise to this centripetal force. All right? And so let's do an example. Well, first of all, I want to kind of show you, in this next example, it says a separation of blood in a centrifuge. I just want to show you how there is very drastically different centripetal forces happening in a centrifuge based upon the mass of a water molecule versus the mass of a blood cell. So I encourage you guys to put those two masses in and see the difference for yourself. This is basically just a rehash of the problem we did earlier with the centrifuge. So go ahead. You can put in the mass of a red blood cell, which is 1 nanogram, 1 times 10 to the minus 9, versus the mass of a water molecule, which is 3 times 10 to the minus 23 grams. And so you can tell from this that there's going to be a drastically different centripetal force experienced by both those objects, causing them to separate. Okay? All right. Let's take a look at an example involving a loop-de-loop, right? Which is any kind of, either a ride or a stunt where you have a track that allows you to move in a circle, right? By pushing off the track, you are essentially staying in circular motion, okay? And the question is, in 1901, a circus performer named Allo Daredevil Diavolo introduced the stunt of riding a bicycle in a loop-de-loop, right? Which I can't imagine being the first guy to ever be the one to try that stunt. It's pretty spooky. Assuming that the loop is a circle with a radius of 2.7 meters, what is the least speed v that Diavolo and his bicycle could have at the top of the loop to remain in contact there? Okay. So to begin looking at this problem, let's start with our actual loop-de-loop. Okay. And let's make a free body diagram. So we know that there's a bicycle here, right? Blah, 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 blah. There's a man on it. Try to make him upside down. Okay, it's not terrible, not terrible. Okay, and now we want to make a free body diagram so that we know exactly what are all the forces operating on this fellow, right? And we know that obviously he's got a weight, right? So gravity's acting on him, right? And we also know that he's pushing off the surface, right? So if he's pushing on the surface got to be pushing back. That's going to be a normal force. He's going to experience a normal force as well, right? Is there any other forces he's experiencing? Well, you can say centripetal force, but remember that normal force is what's causing the centripetal force, right? Okay? So, in other words, we have everything we need right now, and now we can do a Newton's second law analysis of this guy, okay? And so we can say that the summation of forces, right, these are all acting in y, right? So summation of forces in y must equal to mv squared over r. Because this is circular motion, we need to adjust Newton's second law to reflect the circular motion by saying that these forces are going to combine to create a centripetal force, right? Okay, now, in this case, we have n, which is negative, so we have a negative n, right? And we have a negative w going down. We have nothing in the positive direction, correct? Okay. And that all has to equal mv squared over r, right? But it's important to know that if this is centripetal force, right? Centripetal force at this point is pointing inward, right? Centripetal force always points inward, right? So you need to reflect that when you're making this equation. If you're here and you know your centripetal force is pointing downward, that's going to be a negative centripetal force. Whereas if it were down, centripetal force would be pointing up, right? Because it's pointing towards the center, and then it would be positive in that case. But that's beautiful because we can just make this positive, 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 right? We can just rewrite this as n plus w equals mv squared over r, okay? Now the question is, what is the minimum speed v, right, so that the bike would be able to remain in contact with there and you'd actually get around the whole loop without falling and breaking your neck, okay? This is what anyone who tries an experiment like this has to contend with, right? And they need to hire physicists who can do calculations like this, who can tell them the minimum speed they need to get to, okay? Which helps you then design the track, like what radius should it be so that you can even get to that speed, okay? All right, so here's something you need to know in order to solve this question. If this guy's just barely making contact, right? Remember, the normal force is that force of that contact, right? However much the wheels push on the track pushes back. But if you're just remaining in contact, right, there's no more normal force, right? He's just making it around, right? So the surface is not pushing back on him with any significant amount of force, right? So when you're just making it around, you're just maintaining contact, basically that means that n goes to 0, okay? So in this case, in order to find the velocity, all I got to do is solve for this equation, right? Weight is mass times gravity. This is mv squared over r, right? M's cancel, right? And so I just get a very simple equation of the velocity must equal the square root of g times r, right? And in this case, g is, as you know, 9.8, right? And the radius, they tell us, is 2.7 meters, okay? So what is that velocity? All right, this fellow, Allo Daredevil Diablo, must get his bike to a speed of 5.14 meters per second, which isn't trivial, right? That's almost 20 feet per second. That's really fast, okay? Especially for a bike, right? Which is why, as you can see, he needs to start off from this high velocity so that he can gain that velocity required to get him around the loop-de-loop. Okay? So what did we do here? As a recap, well, we made a free body diagram to show that the only forces acting in this guy are the normal force of the track pushing down on him and his weight. Okay? And we know that the sum of those two forces contribute to create this centripetal force, mv squared over r, here, right? We know that the normal force goes to 0 because I'm just making contact, right? So you're not really pushing off the track as much anymore. That goes to 0, leaving weight mg equals mv squared over r so that I can calculate the velocity required to get around here without seriously losing touch with the track. Okay? And I think I'm going to leave it there for now. And in the next video, we're going to talk about a Ferris wheel. One of the first Ferris wheels, the Grand Roue de Paris, which was at the 1900 World Exposition in Paris. All right, I'll see you there.